In the last video, we were just looking at if you look up at the sky, you might see stars. And stars are giant nuclear fusion reactors. That's what those are. And every time that they convert hydrogen to helium, you end up with energy. And that energy is in the form of light. By the way, stars do other complicated things. It turns out they can convert other heavier things into even more heavy things. So it's not just hydrogen to helium, but it's the main one. It's what happens in what we call a main sequence star. Now let's take a look then back at this one here. So this one right here, if we look at these stars, each one of these right here is a star, each one of these dots here. So I'd like to sort of focus on one of them right here. This one right here, this one has a really funny name. Remember, this is part of Orion, this one right here where you can see this is the hunter guy right here. This star right here has a really cool name. Now I'm probably massacring how it's pronounced. If you're Arabic, you could probably pronounce it better than me. But at least in English, we call this Beetlejuice. Now you might have seen the really sort of bad 80s movie called Beetlejuice. It was spelled differently, and it didn't at all have anything to do with this star though. But it's a funny name, Beetlejuice. It sounds funny to say. But that one right there is a really interesting star, just to give an example here. So this star right here is what we call a red supergiant. So you see that, it looks red. And astronomers are pretty direct. We say it's a red star. Now it's a big star, so it's a giant star, but it's bigger than a giant, so we call it a red supergiant. That's actually kind of funny. Now this one right here, it is huge. Now how huge do we mean? Well, it is so big that if you were to replace, now this right here, let's just assume this right here is the sun here. So let's say that right there, let's just do this in sort of distance here. So as you go out, if this is the sun, and I don't know if you know your different planets right here that go along, but this first one right here is called Mercury, and the next planet out is called Venus. That's because there are other rocky bodies that orbit around the sun. So the closest one's called Mercury, next one's called Venus. After that comes the Earth. Now they're not even spacing like this, but just to show you here. So Mercury, Venus, Earth. After that comes Mars. And after that is Jupiter. And after that is Saturn. And after that is Uranus and Neptune and Pluto and all the other rocky things that are out there. But just to say that if we were to replace our sun, so if you could sort of swap our sun with this one right here, if you could just sort of, you're some sort of god or some sort of omnipotent being and you could replace them, it is so big, it would completely envelop Mercury and Venus and Earth and Mars, and it would be most of the way out to Jupiter. So it is that huge. Isn't that amazing? So this star right here, we would be in it. So thank goodness that we're actually not there. This star is that big. I think that's really crazy to think about. And in fact, we expect it to go supernova anytime soon. So what do I mean by supernova? I mean that it'll eventually explode. And again, a nova is an explosion, but an even bigger one, we call it a supernova. So you see, in astronomy, we're quite descriptive in what we're doing. And I think it's really interesting with this star right here. So there are other stars out there. They're not just like our own sun, but I'm pretty happy to have our own sun. In fact, this brings up, I think, my favorite joke, but one of the worst ones ever. So those who know me know I really enjoy stupid jokes. So my favorite one is this. Are you ready? I was so bright, my father called me sun. Sun, S-U-N. Okay, that's bad. Let's move on. So we have something else called a light year. This is something else that I look at when I think of this picture right here, with all these dots right here, which now we know are stars, and that means that they're fusion reactors. We know that they appear to rotate because the Earth is actually spinning around. But there's another thing that blows my mind whenever I think about all this. And that's this thing that I'm going to call the time machine. So this is really what's going on here. That, the night sky is a time machine. Now, I'm not exaggerating here. I'm not saying it's like a time machine. No, you really are. You're looking back in time. This is what I want to show you here. This is what's really crazy about it. So I think this is really, really cool. So when you're looking at these stars right here, you're seeing the stars not as they are right now, but as they were a long time ago. So this is, in every sense of the word, a time machine. Now, how can that be? Because we have something called a light year. And actually, this explains a little bit about the distances. Now, just imagine if you're trying to measure the distance to something, you could have what we call a meter stick. or if you're an American, I guess you call it a yardstick or whatever. And you could measure, this length. So that's 1 meter. Now the problem is, what if you have a whole bunch of those? Okay, well in the metric system, we have a system. We can say, okay, if there's 1,000 of these, then we call it 1 kilometer. That's great. But the problem is that's not even big enough. We need lots of those. So what we've done in astronomy, we have, because these numbers are so huge, we've actually said, all right, let's go totally crazy. Let's think of a really big unit. So we have what we call a light year. So what a light year is, I'll just explain it here. So a light year, this is what's really cool here. That is the distance that light travels in 1 year. So this is actually pretty crazy here. So what do we mean by this? What we mean is that, well, light goes really fast. I mean, how fast does light go? Light goes this fast. I mean, light is very fast. I mean, just to make a little bit more sense here, light is so fast, in fact, if you imagine 1 kilometer, I mean, can you imagine that in your head? Maybe you walk a kilometer each day, or, you should have some inkling, some idea what a kilometer is intuitively. Now, let's take that and try to make it even more. So the speed of light is this. It's not just 1 kilometer, but 300,000 kilometers every 1 second. So, I mean, that's hard to imagine, 300,000 kilometers, isn't it? And imagine that in 1 second, light goes whoosh, 300,000 kilometers every 1 second. Now, we often say, we call this speed of light, we actually call it, so that was this letter C that we had before. And we actually say that's 3 times 10 to the 8 meters per second. But it turns out that's the same thing as 300,000 kilometers per second is this scientific notation here. So that is really fast that light goes. And so if you were light traveling that fast, so 300,000 kilometers every 1 second, and you were doing that for 1 whole year, that is the distance we call a light year. So that is a huge distance. Now, we even have a little symbol for it. We can say 1 light year. This is actually the symbol we use. So 1 LY. And that actually has a number. I mean, in case you're wondering how many meters that is, well, it's lots. We have a compact way to say it, but it's I think it's a 9.46 times 10 to the 15 meters, which means if you wanted to really figure this out, you'd have to write the number 9 and then 4 and then 6, and then move this decimal over 1, 2, and then just start adding a bunch of zeros. So basically, you'd have to move your decimal over to the right by 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This would be this many meters. So lots of meters. So see, that's at least a nice unit to use. Now let's maybe go back to this one over here. So what about Betelgeuse? How far away is that one? Betelgeuse is around, so the distance is around 650 light years, and that's considered close. So what that means is that the light you're seeing from this particular star right here, it left Betelgeuse 650 years ago, and it took it that long to get to you. Which means, if we're actually looking at this star, so this right here is Betelgeuse way over here, really, really, really far away from us. Okay, let's say that's Betelgeuse. I suppose I probably should have drawn it in red, shouldn't I? There we go. So that's Betelgeuse, let's just say. And then here's the Earth, really, really far away. This is the Earth. Well, what it means is that the light from there actually took 650 years to get here. So that's how long it took the light from Betelgeuse to get to Earth. Now, I said before, we're expecting it to blow up or go supernova. And what that means is that if it does blow up, maybe it blew up 649 years ago. And that means that we're only going to see the explosion maybe tomorrow. That would be really cool, by the way, because it would probably be quite bright. So I think it's really, really neat to think about is these distances. Now, in fact, with light years, we have something else really cool. I mean, we have our own solar system. So let's say this right here, this is the sun. Whoops, I need to draw it in black. So this is the sun, let's say, so that's our own. And then we have the Earth going around. We actually have, now the Earth actually orbits around like this right here. We have a unit that we actually call 1 astronomical unit, so AU. And 1 AU, it turns out that this distance right here is about 1 That's 1 light minute. That's because this isn't actually that far. Whoops, sorry, not 1 light minute. Sorry, that's my mistake. It's 8 light minutes. So what this means is that it takes light from the sun 8 minutes to get to us, which means when you look up at the sky today or tomorrow and you see the sun, you're seeing it 8 minutes ago. Isn't that awesome? So that means that whenever you're looking up at the sky, you're looking back in time. You're looking at these things as they were a long time ago. And the farther out you're looking, the farther back in time you're looking. And this is why astronomers can tell how old the universe might be. We can do all sorts of neat things. Now that's 8 light minutes. What's kind of cool is the next planet out. So of course there was Mercury and Venus that were there, and then there's Earth. The next planet out is called Mars. Maybe I'll draw it sort of reddish, because it's reddish in color. So this one right here, Mars, as that one right there goes around, it has a distance of around, so this distance right here is around 1.5 astronomical units. Now, this is really interesting because we have robots that are driving around on Mars. So what it means is that, what if you're on Earth and you want to try to send a signal to that robot on Mars? This is happening today. I mean, there's a robot called Curiosity. It's the Mars Science Laboratory. Let's say we're at our closest together, because remember, Earth goes around like this, but Mars goes around like this. They don't always follow each other. So you might have the Earth over here and Mars might be way over here, because each of them is free to go around their circles here. And it turns out that when we're at our closest, for example here, we're at 0.5 astronomical units away from each other. If that's the case, well, if 1 AU is 8 light minutes, that means that our distance to Mars, it might be only 4 light minutes, but it can be even worse. It can be a lot longer. What if the Earth is way over here? So if the Earth is over here and Mars is at the other end, it could be as much as, well, let's see, this right here would be around this way right here. So this right here would be 2.5 astronomical units. So 2.5 times 8, that would be, what, 20. So that means that Mars could be between 4 to 20 light minutes away. Now, what does this mean? This means that if you're driving this little robot, let's say, or if scientists want to give a command to the robot that's sitting on Mars, you have to think 4 to 20 minutes ahead of time. You can't just be watching the robot drive and say, hey, stop right now, because it might take it 20 minutes to get the signal. Maybe it already drove off a cliff or ran into a rock or something. So you really have to think about these distances. That really makes a difference. So again, the thing that blows my mind is that we're looking back in time. How cool is that? Now, we also might see a shooting star when you're looking at the sky. I don't know if you've ever done that, but if you're ever looking up at the sky and you see what we call a shooting star, what we really mean here is this, that this is just a piece of dust. This is usually what a shooting star is. It's usually a piece of dust entering our atmosphere. And it just heats up. That's really all it is. It's not really a moving star. It's actually just a little piece of dust, and in fact it's very likely the size of a grain of sand. That's what most of them are, about that size. Pick up a piece of sand, and that's very likely what a shooting star is. So it's usually just a piece of dust entering our atmosphere, and it just heats up, and that's why it glows. Now, why is that? Well, that's because we have the Earth like this right here. Let's just say we draw sort of a side view. This is the Earth. This is our rocky planet we live on. But it turns out we have our atmosphere. We have this little cushion, this little layer. And this layer right here, that right there, that's our atmosphere. That's this area of gases that we really need. We have air, for example. So that has, oxygen and has something called nitrogen. And we need all these things. These are things that we need in order to breathe. So lots of other things in the atmosphere. Sorry, my little thing right here went a little bit crazy, my pen. So we have this. So what happens is this. Let's say we do a top view right here of what's going on here. So here we have the sun, like I've been drawing before. And let's say that then we have the Earth here. And the Earth goes around in its orbit, like this, like that. Let's just say this is a top view here. Well, what happens is there are things called comets. And there's asteroids and all sorts of other objects. Now these objects might come in, for example, whip around the sun and then go back out. They have like really big weird orbits. So maybe it's a comet. Now a comet is just a bunch of dust and ice. Well, as that comet gets close to the sun, a lot of stuff sort of melts off and flies off, and it turns out a lot of the dust does too. So imagine then this comet is leaving a whole bunch of junk in the way. I mean, it leaves the junk everywhere, of course. So just a lot of dust and, just rocks and dust and junk left in its path. So what happens with the Earth? Well, we run into those. Maybe we actually cross its path here, or maybe we cross it here. I mean, this is a 3-dimension, so it doesn't mean we have to cross it twice necessarily. But if we go around like this, we might actually run into a bunch of those. So when that happens, we can predict and we can say, aha, we're going to have a meteor shower, because a shooting star is sometimes called a meteor. So a meteor is again just a shooting star. So these are all they're the same names for this, different names for the same thing. So if we know, for example, as we come through this right here, we know that we're going to cross the path of this comet. So we can predict and say there's going to be lots more pieces of dust that are going to enter our atmosphere. What happens is when they hit our atmosphere, they get really hot, and so they give off light. Now some of them might go like this, for example. Some of them might just come right in like this, so you'll just see a little dot. What if they go like this though? What if one's at a low angle like this right here? Then it's going to seem like it lasted longer. So you see that as they enter our atmosphere from here to here, it's going to be really bright. So if you're sitting there looking up, you're going to see this bright dot go like this. Now, those are most of them are. Most of them are really small. But it's possible to have really big ones. In fact, in February 2013, there was a really big one. So I'm going to open up my computer here and show you this. So this one right here, this is what happened in Russia. And I'm just going to try to get rid of all the stupid ads here. So take a look right here what happened. Look at this. So this guy right here, because everybody in Russia seems to have dash cams. So then they're recording what they're actually doing when they're driving. But look at this thing in the sky. Look at it. Isn't that amazing? Oops, we have another ad. Thank you, YouTube. So if we look at this, then we'll see, I think, a few different views of it. So this is, again, people who are just driving around, and all of a sudden they saw really bright things in the sky. Look at that one. I mean, it's obviously from different angles. But look at that. It's like fire across the sky, because it was a really big one. And that one actually went, at an angle that made it to where it lasted a long time. Isn't that amazing? So again, if you're just driving around, maybe you saw this crazy bright line like this. So this is possible. We see these. Now, usually they're really small ones. That's what you'll see at night, for example. You'll see tiny little pew across the sky. Once in a while, there's big ones, and sometimes they're huge. I mean, we think that there's a gigantic, ridiculous one that actually killed off all the dinosaurs. And in fact, that is going to be related to our story about astrobiology later.